Today we're going to be taking into a limit. Hey, I'm Mr. Klein in a hat again. This is fun. We're going to be taking it to the limit with one particular limit. That's the limit of this function right here. The limit as x approaches 9 of 9 minus x divided by the square root of x minus 3. Recall that this right here, 9, is called the limiting value, and I'll refer to this function right here as f of x. One of the things I'd like you to know about functions is that there's 3 different ways that we can evaluate them. We can evaluate them by looking at a graph. We can evaluate them by looking at numbers in a neighborhood of the limiting value. And we can also look at them algebraically. So we're going to go through all 3 for this function, and we're going to go a little bit out of order. We're going to start with the numerical approach. One quick note, ladies and gentlemen, we're going to be using the TI-84 calculator quite a bit for what we do today. Please do everything that I do on your calculator because it will make sure that you know how to use it. So step number 1 is to go to y equals and type your function in right there. You can pause the video and do that. Once you've typed it in, we want to look at some values in a neighborhood of 9. Now, what do you think is going to happen if we actually type 9 in? One way we can do that is we can go alpha trace y1 of 9. And it's going to tell me error dividing by 0. So that tells us that at 9, this function must be undefined. So what I'm going to do is I'm going to pick some values that are in a neighborhood of 9. Maybe I'll start with 8.9. It's a nickel away. And since I'm going to do a bunch of values, let's do it this way. Hit second and then hit table set. And then you want to make sure that your independent variable is set to ask. And if it's set to ask, you can hit second table and you'll get a menu that looks something like this. It's empty. If it's not empty, there's like, I don't know, a 12 right there. All you have to do is move the cursor on top and hit delete, and it'll go away. So I'm going to put 8.9 in. And the y value, by the way, this should be x, this should be f of x, is this, negative 5.983. Well, that's not a nice clean number. Let's see what happens if I go closer. Let's go 8.99. One of my favorite prices. That gave us negative 5.998, which is really close to negative 6. I'm thinking negative 6 might be the limit. So now I'm going to go 8.999. And it actually says negative 6 on your calculator. Now, one thing you got to be careful about is that it's not negative 6. If you move that cursor onto the actual button here, you'll see that it is just a number that's so close to negative 6 that the only thing the calculator can think to do is round it up. But the truth is that when we are 1/1000th away from 9, this comes out to be negative 5.999. So what can we conclude from the work we've done here? Well, we can say that as we're approaching 9 from the left side, because these are only values that are smaller, the y value appears to be approaching negative 6. Or in other words, the limit as x approaches 9 from the left of our function is negative 6. Now that does not mean the limit exists, right? Because we also have to look at what's happening from the right side. So if I was going to play a similar game from the right side, what would be some good numbers to use over here? For symmetry's sake, symmetric to the 8.9 might be a 9.1, and then a 9.01, and then a 9.001. Try popping those into your calculator and see what you get. I got these values right here, a little bigger than negative 6, or a little more negative than negative 6. almost -6, and really stinking close to -6. So we can say that the limit as we approach from the right side is -6. Now, since from the left side we're getting a -6 and from the right side we're getting -6, what conclusion can we make from this? A and B imply that the limit as x approaches 9 of f of x in general is -6. There's our answer. All right. Now, let's suppose we hadn't done that. Let's suppose instead we wanted to look at a graph. I want to remind you that on your calculator, you can get a graph really easily just by hitting the window and picking a good domain. Now we want to see the value somewhere at 9, around 9. So I'm going to go from 0 to 12. Notice that 9 is captured in that region. And then I'm going to hit the zoom button, and I'm going to go to zoom fit. I can't remember whether I've explained this already, but zoom fit will automatically work out a Y range to go with the X domain that you've given it. So I'm going to hit that, and the calculator is going to pop out a little graph for us. Looks like a square root function. I notice there's a little space right there. That means that there must be a hole. Okay. Now we know that this value right here must be at 9, this hole, because we already plugged in 9 and found that the function is undefined there. So obviously it would not be able to graph a value. Quick note that your calculator does not put these removable discontinuities into its images. You have to know that that's supposed to be a hole. Now, if you didn't know what the Y value was that goes with it, you'd hit the trace button, and you get the little space invader dude, and you would go, and we can see that on either side, it's getting really close to -6. So we could identify the limit that way. Third way is the algebraic method. So for this one, we're going to assume that we do not have a calculator. Goodbye, old friend. We have enjoyed many good times together. And instead, we're going to say, all right, I've got this guy right here. And I already took the first step, which was to plug in the limiting value. Plugged in the 9 and found that we got 0 over 0. Uh-oh! It's an indeterminate form. Now, this time, factoring does not seem so obvious, does it? So there must be another way to do the algebra on a problem like this. And the answer is something that rhymes with schmonjugate. That's right. It is conjugate. What you're going to do is you're going to take the conjugate of the square root term. And the conjugate is the same binomial, but with a different sign in the middle. So since we see a minus right here, we're going to multiply by roots of x plus 3. Now, if we do that to the denominator, we also have to do the same thing to the numerator. And why do we have to do that? Well, it's because when you multiply a function by something, you change the function. And you're not allowed to do that unless the number that you are multiplying by is 1. So we take this and we multiply it by our conjugate 1, and that's going to give us something new. Now, why do we do that? Well, it's because it deals with the square root. Check out the denominator. D for denominator. I want to multiply the square root of x minus 3 by the square root of x plus 3. That's going to give me x, 3 roots of x, negative 3 roots of x, and negative 9. And this and this are going to cancel out, and I'm just left with x minus 9, which means we could take this expression up here and we could rewrite it as the limit, x is approaching 9, of, in the denominator, we now have x minus 9. In the numerator, I don't want to multiply these out, and you'll see why in a second. So only multiply the side that you think you're fixing, the side where you chose the conjugate, the denominator in this case, because it had the root. 9 minus x times roots of x plus 3. And I'm looking at this guy right here. I'm saying to myself, can I cancel those? What do you think? Can we cancel those? Is that allowed? Well, you can only cancel if they're equal to 1. If I plug in a number, do I get 1? Give me a number, any number. What was that? 2? Okay, let's plug a 2 in. If I plug a 2 in here, I would get 7 over negative 7, which is equal to negative 1. Give me another number. 4? Okay, 4. Let's plug 4 in. 9 minus 4 is 5. 4 minus 9 is negative 5. 5 over negative 5 is negative 1. It turns out that because these are opposites of each other, see how the terms have been reversed? 1 divided by the other is always equal to negative 1. Therefore, we can say this is equal to the limit as x approaches 9 of negative 1 times the square root of x plus 3. And now, if we plug that 9 in, we get negative 1 times roots of 9 plus 3, which is 3 plus 3 is 6 times negative 1, negative 6, which, if I'm not mistaken, is the same number we got right here and the same number that we got right here. Cool. So we're on the back now, and because we're on the back, I've turned my hat backwards. It's fun. And this is going to take us through the way you deal with all of these algebraic limits. So step number 1, always plug in x equals c. If you get a number, guess what? You're done. Second thing, if you get 0 over 0, then you must, we'll call it reorganize or simplify the function before you plug in again. And so let's talk about all the different ways that you can reorganize. One right here is factoring, which we practiced last class, so I won't go through that again. A second way is to find a common denominator. So here's an example right here where we could find a common denominator for the x and the x squared plus x. Notice that this one factors into x plus 1. What that means, little side work over here, is that if this fraction is 1 over x times x plus 1, this one is 1 over x, we could multiply this one by x plus 1 and x plus 1. Oh, there's a subtraction. Therefore, come back up here. This is the limit as x approaches 0 of x times x plus 1. And then in the numerator, we have this plus 1 minus 1, so it's just x. Now, this should make sense to you because our limiting value is 0. And if you have a 0 there, you know you're looking for something that has a factor of or a root of 0. And the only thing that has a root of 0 is x itself. So we can now take these two terms and cancel them. That gives us the limit as x approaches 0 of 1 over x plus 1. I plug in the 0, and I get one of my favorite numbers. The limit is 1. Moving along. Third thing you can do is you can multiply the numerator and the denominator by a conjugate. Notice that that's the same thing that we did back here. Notice that when we did it, we ended up with factors that have a root of 9. Okay, so you're always thinking of something that's going to have that as a root. Now here is kind of a tricky one. This is one where we're going to have to reorganize. Here's my first question for you. What do we get when we plug 2 in? Now let's see. 2 would give us a 0 up here and a 0 down here. Uh-oh. It's an indeterminate form. Well, we know that we must need to cancel something. Can we cancel an absolute value of x minus 2 with an x minus 2? Well, that would be legal if this is always equal to this. Do you think that those two things are always equal? One way to show that they're not always equal would be to come up with an example of a situation where they are not equal to each other. For example, what if we plugged in 1? If I plug 1 into this side, I get a negative 1. If I plug 1 into this side, I get a absolute value positive 1. So I found an example where they are not equal to each other. Therefore, they are not in general equal. We can't cancel them. Rats. That was going to be easy, wasn't it? I'm back. Now, what could we do? What could we do? Well, let's think about what absolute value does. Absolute value makes things positive. Can you think of something else that makes things positive? What about squaring, right? Squaring makes things positive. So would this be equal to this? Would those be the same? The answer is yes, those are always equal to each other, 100% of the time. You will not be able to find an example where those are not equal. Well, as long as we're moving along, what about this one? I see a cubed right here. Is this equal to this? That's a 2. The answer to this one is once again no. And the reason is no, it's no is like, I don't know, pick a number, pick 1 again. You pick 1, you'll get a different value over here than you will over here. So this little trick right here works anytime you're going to have an even power, because it's even powers that make a term positive. So here's what I'm going to do. First, I'm not going to square this thing. You are not allowed to just square functions. It's illegal. If you could, I would take my salary and I would square it. And then I would work 1 more year and you would never see me again. Instead, here's what we can do. Take this numerator. Some of you know what I'm thinking here. Take this numerator and break it into 2 chunks. Now, what good did that do us? Can we cancel these 2 things? No. Instead, here's what we can do. Remember this guy? This rule over here says I can replace him with him. So if you rewrite the expression this way, we can now say the limit as x approaches 2 of this times that over this. Okay, so this became this. And now that's good because at this point we can actually cancel one of these with one of these because they're both x minus 2's, which means what we're left with is the limit as x approaches 2 of one of these and one of these. Plug in the 2 and you're going to get 0 times 0, which is 0. Okay, that is the game, ladies and gentlemen. You've got a pretty challenging assignment in front of you. So why don't you go get cracking on that, and I will see you later.